Hello everyone, welcome back. In the last class, we basically discussed about the Rance equations, how it is derived, and we also saw that once you derive the Rance equation, you get an unknown term which are the Reynolds stresses, and there are 6 independent stresses, and you need to model them. Okay. And one way to model is that you just use the Reynolds stress model, where you have to derive or you have to somehow construct 6 different equations for, let us say, u prime. So, there are 6 stresses which are basically u prime square bar, v prime square bar, w prime square bar. These are the Reynolds normal stresses, and u prime v prime bar, u prime w prime bar, and v prime w prime bar, shear stresses. So, you will have to basically get 6 dynamical equations for all of these, because every iteration they will change, right. Just like you have the dynamical equations for the density, which is the continuity in the compressible flow, or in the momentum you have dynamical equations for u, v, w, okay, 3 velocities in the incompressible flow or the compressible flow. Similarly, you have to have 6 different equations for this. There will be a term of unsteady term, there will be a convection term, there will be basically dissipation of these stresses, production of these stresses, and so on and so forth. Right. So, if you want to have 6 different more dynamical equations apart from the Navier-Stokes equation that we have. So, you get you solve these equations, get these quantities, put in the Navier-Stokes equations, the Rance equations. Okay. So, that approach is called the Reynolds stress model. Okay. The other thing what we said is that now we are not going to solve 6 different equations. Okay, what we are going to do is that you will say that rho u I u j u prime bar u prime bar u j prime bar will be related to quantity, single quantity called the mu t, which is the eddy viscosity, and then we S I j bar. Okay. What is S I j bar? Is basically del u bar by del x j plus del u I by del x j plus del u j bar by del x I. Okay. These are basically the symmetric stress tensor, and that you can directly get because you have been solving for u I bar, u j bar, and so on and so forth. And then we had some corrections due to the turbulence kinetic energy, I think okay, delta I j. Right. So, now the question that we had that you have to get 6 stresses gets reduced to that what is the value of your mu t. Okay. So, if you can find the mu t, you can find all these 6 quantities, okay, because this will depend on u I u prime bar. So, you can the S I j bar is also a stress, right. So, this is basically if you put I equal to j and 1 both are 1 1. So, this will be T 2 du by dx. Okay. This will be du by dx plus dv by dy. Okay. This will be du by dx plus dw by dz. Right. Similarly, you will have 2 del v by bar, all will be bar, okay, because we are talking about this bar, del v bar by del y, and 2 del w bar by del z. And similarly, you have similar term here, okay, and finally, there will be term of v and w. So, that will be del v bar by del y plus del w bar by del z. Similar term will come here, and this term will also come here because of symmetricity. So, if you want to make a one to one correlation, so this is basically my minus rho, this is u prime bar square, u prime v prime bar, then u prime w prime bar, then v prime bar square, okay, and then v prime w prime bar, and v prime u prime bar, and this is w prime bar square, okay, w prime square bar, and then you have this w prime v prime bar and w prime u prime bar, right. So, we know all these things, okay, from your simulation. We just multiply. So, what we will do, we will just multiply this entire thing by mu t, and for this you will have mu t multiply by this, for this you will have mu t multiply by this, and of course, you will have this term which needs to be cancelled out. Okay. So, the question boils down to how do you get this mu t, the eddy viscosity, right. So, the eddy viscosity basically depends on basically the velocity scale and the length scale. Why? So, if you look at now, we will go to some heuristic arguments. Okay. We will not go by the theory. There is no theory to basically derive this eddy viscosity model or the dynamical equation for eddy viscosity, but we will go with some heuristic model. So, one thing is that we are saying that my eddy viscosity is somehow similar to the kinematic viscosity that we have. Okay. That is the first argument. Secondly, I mean it is much higher than in the turbulent fluid, is much higher than the kinematic viscosity, because as we discussed earlier that it leads to the mixing, right. So, how do we get this viscosity? So, we have this mu t, which is the eddy viscosity, and just like we have this dynamic and kinematic viscosity, we will also define this kinematic eddy viscosity mu t by rho as nu t. Okay. And what is the nu t? Unit of nu t? This is meter square per second, right. So, this is the kinematic viscosity, just like you have the kinematic viscosity nu is equal to mu by rho, and the unit of that is basically meter square per second. Similarly, the kinematic eddy viscosity also is the unit of meter square per second. Now, you can write this meter square per second, and why I am doing all this? Because I have no information of how to compute this, but I want to basically base my argument on the observations that we have, the value that you see in the experiment. Okay. From that I want to basically construct a model. So, my eddy viscosity can be obtained, the kinematic eddy viscosity can be obtained by considering a velocity scale, which is unit for that is meter per second, and a length scale, which is meter, right. So, if somehow I can find out my velocity scale, which I call it as u 0, and length scale as L 0, I can find out my nu t, right. Now, for u 0 the velocity scale, one thing that we can think of that how do you get the velocity scale, like something which represents the turbulence, right. So, we know that my turbulence kinetic energy half k is equal to half u prime bar plus b prime bar plus w prime bar, right. So, what is the unit of this? This is meter square per second square, right. So, I can take my velocity scale u 0 as basically square root of k, because it is characterizing the turbulence, okay. And it will be helpful in basically whenever you want to compare against the experimental data, because it is somewhat giving me the picture that okay, the turbulence is there, and from the turbulence kinetic energy we are getting this velocity scale. Okay. Now, the question is how do you get the length scale, right. So, the length scale is typically, let us say if you are trying to simulate flow in a channel. Okay. So, your largest size is basically this, okay. So, and then maybe smallest is this, you take something in between. Okay. So, that is called inertial length scale, and that will be your typical eddy size, okay. So, an average of these eddies, okay. So, that is the length scale. Okay. Now, so these arguments are fine, but we have to somehow put it in the framework of how we solve the equations, right, because this turbulence kinetic energy will change with time, depending on, let us say you have a flow which is going like this, okay, there is a eddy size is different here and eddy size is different here, it may also change with time, right. So, we have to somehow in the put in the framework of dynamical equations. So, that is where you have different models come into picture, okay. You might have heard about this k epsilon model, k omega model, SST k omega model, okay, and so on and so forth. So, they are basically what they are trying to do, they are trying to basically get the eddy viscosity, and the argument comes from that we have a length scale and we have the velocity scale. Okay. So, let us look at this k epsilon turbulence model. So, k, as I told you that it represents the velocity square in a more precise way. Okay. So, that has to be there. Okay. The second, we are saying that okay, we are talking about how the turbulence is getting dissipated, at what rate it is getting dissipated. Okay. So, that is called epsilon, okay. And you can work that out, the unit of this epsilon will be meter square per second cube, okay, because it will depend on the gradient, not on the gradient, but basically the gradient is square, and then you will multiply with the viscosity there. Okay. So, the unit of that will be meter square per second cube, correct. So, now we have something on meter square per second square and meter square per second cube. The idea is to get some quantity which is basically meter square per second, right. So, how do we get that? So, why? Because this is the unit of nu t, right. So, how do you get this? You have k, which is meter square per second square, and dissipation rate, which is meter square per second cube. right. So, what we will do? We will do k square, okay, that will make it meter to the power 4 to the power s to the 4, this is k square, okay, and by epsilon. So, this is k square epsilon. If you do, this is meter square for second to the 4, sorry, m 4 s 4, and this is s q by m square, sorry, yeah, that is correct. So, this will become m square and this is s, this is meter square per second, right. So, if you know this k and if you know the epsilon, okay, we can construct my quantity which is basically mu t, which is k square by epsilon, nu t, sorry, not mu t. But then there is also a constant which comes into picture, which comes from the experimental observations. Okay. This is the quantity c mu. Okay. In fact, you can get the argument of how to get it. Okay. This is around 0.09. Okay. So, this goes on the definition of how this isotropic, if the stresses are isotropic, how will they contribute, right. But I will not go into the detail, this is not a proper CFD course. But yeah, I just want to say that this coefficient which comes from two kind of thing. One is that you look at the picture in your in let us say what you get from the wind tunnel, you calculate the turbulence kinetic energy, you calculate the dissipation rate, calculate the k square by epsilon, okay, and you want to use this in as a mu t, okay, then you will see it is not matching. Okay, so, there is something which is missing, there has to be a factor, and that factor is the c mu. In fact, there are many more equations, there are many more such numbers like c epsilon 1, c epsilon 2, which will be, which has to be fixed, and they have to come from the experiments, okay, or maybe the DNA simulations. Okay, so, once you fix this, you can also actually write in terms of the kinetic energy scale and the length scale, right. So, this is already that velocity scale is k to the power half. So, the length scale is L 0, right. So, L 0, if you reorganize these things, you can write that L 0 is can be given like this, L 0 equal to c mu k to the power 3 by 2 by epsilon, right. So, from both the k and epsilon we get the length scale, from the kinetic energy we get the velocity scale, right. So, u 0 is square root of k to the power half. So, once you have both of these, you can basically get the viscosity using this formula, right. So, instead of talking about the u 0 L 0, now we will talk about k and epsilon. Okay. So, we need this k and epsilon will change in every iteration. So, you need to have this dynamical equations for del k by del t and del epsilon by del t, right. These dynamical equations will solve the k and epsilon at every iteration. From that you calculate this nu t, okay, and this will be put in the momentum equations in the Navier-Stokes in the Rance equations, right, and that is how you will do the simulation. So, just take a look into this k and epsilon equation. This is the k epsilon, and you can see there is a temporal term, there is a term which is like advection like, okay, and then there is a diffusion term. Okay. This is all inspired by the original equation that we have. Any advection equation you will take, or advection diffusion equation, you will have an advection and temporal term and diffusion term, and there are some terms which are coming from your from the observations that we have. So, we have the sources and sinks terms, where this is a production of kinetic energy P k, then the dissipation and so on and so forth. Okay. It is not derived completely from the first principle, although you can take the momentum equation and then subtract the. So, basically you can take the turbulence kinetic energy equation d k by d t and subtract the mean turbulence kinetic energy, and you can get this equation in terms of k, but then you will have some more terms which are being added here. So, okay, so this cannot be derived directly from the first principle. Okay, there are some extra terms which are added here, and the dissipation equation that we have, you can see that it is completely modeled based on the T k equation. You have temporal advection, diffusion, sources and sink. The k is replaced by epsilon here, okay, everywhere. Okay, you can see this k epsilon by this replaced by this, and this the sources of sinks are also accordingly modeled here. Here this is P k, this is P k epsilon by k, and there is a quantity which is C epsilon 1. Similarly, this rho bar epsilon, that will be epsilon square by k C epsilon 2, okay, and then just like we had this S k, we have S e S epsilon, right. So, these are these equations are basically modeled equation, I would say. I mean, they are not derived from the first principles. Okay, but what they give is that if you have the proper value of this epsilon 1, C epsilon 2 and so on and so forth, okay, they will give you the value of k and epsilon. From this we will calculate the nu t, and that will give you this rho u prime v prime bar, okay, or rho u I prime u j prime bar, okay, and that you put in your every iteration in the momentum equation, and that is how it runs. So, now instead of solving only your let us say in incompressible your continuity and 3 momentum, okay, we are also solving 2 more equations, one is for one for k and another for epsilon. Okay. So, total number of equations we are solving in RANS are basically 4 plus 2 6 equations, okay, if you are using k epsilon model. Okay, there are 3 equation model, 4 equation model, in which accordingly your number of these equations will change. Okay, these are basically RANS equations, and then you have extra equations for the modeling of the turbulence. Okay, so, you may think that because you are solving the more number of equations, it will take more computing power, but then you are solving for the mean flow, you are not basically going to every single small and big eddies. So, that means naturally your grid size requirement is very less in the RANS simulation. Okay, so, yeah, so far so good, but what happens when the flow is compressible, that actually makes the things even more complicated, right. So, why is because now rho is also varying. Earlier rho was constant. So, we had this quantity rho u v. So, we had taken rho as constant and you only worked on u v, okay. Basically rho is not changing, but that was incompressible. Now, when the flow is compressible, you have to also look at the fluctuation in the density, okay. Now, rho is rho bar plus rho prime, and if you use the original Reynolds averaging approach, this is how it will look like, okay. And then you will have bar on top of that, okay, rho bar plus rho prime, this is rho, u is u bar plus u prime, and v is v bar plus v prime, okay. And no correlation will go to 0, okay. So, you have basically now this term will multiply rho u v, only thing that will go to 0 is rho bar prime equal to 0, okay, u bar prime equal to 0 and v bar prime equal to 0, any time multiplying that. But now you have basically many correlations, these are the basically double correlations, this is rho u bar u prime v prime bar, rho prime v prime bar, rho prime u prime bar, none of these will go to 0. Okay. So, instead apart from this u prime v prime bar that we are seeing in your in our incompressible equation, we also have this rho prime v prime bar, okay, how this density fluctuations are interacting with the velocity fluctuation in the x and y directions. Okay. And then we also have the triple correlation rho prime u prime v prime bar. So, this has made the things very complicated, okay. The number of stresses also increased, and if you want to put this in your Navier-Stokes equations, you will have to basically model all those things there. Okay. So, fortunately, there is a way to basically reduce this complexity of these equations, okay, and that is called the density weighted time averaging or the Fabry averaging. Okay. This is a trick. So, instead of now doing the averaging for only u, now we will do the averaging for rho u, okay. And same argument that we had for the Reynolds averaging, we will have basically rho u for a very long time, this is all quantity rho u, okay, and take for a very long time, okay. And then we will have a line which is representing rho u bar, okay, and we divide it with the rho bar. So, this is rho u, and let us say you have another one which is basically rho bar. So, you take this rho u bar by rho bar, okay, and that will give you another averaging which is called the u tilde, okay. This is called the Fabry averaged quantity, okay, Fabry averaged quantity. Yeah. So, this is a trick and there are some rules with this Fabry averaging. So, like we were doing that u equal to u bar plus u prime in the Reynolds averaging, and we said that my u prime goes to 0, right, if you take the mean of the u prime. Similarly, we can write this u in this particular incompressible case as u bar or you call it u tilde plus u double prime. Okay. This is the Fabry average quantity which is the density weighted average and plus this is the fluctuation which is coming out because we have taken the density weighted average, right. So, now we are saying that u double prime tilde will go to 0. Okay. This direct time averaging and this the density weighted time averaging are different. Okay. And then there are some rules you can take a look here. For example, you will have this comes from this the same argument rho u double prime bar equal to 0, u prime tilde equal to 0, but u double prime bar is not equal to 0, u double prime tilde equal to 0, but u double prime bar is not equal to 0, and there are some other things you can derive. So, this is directly because u tilde is equal to rho u bar by rho bar, right. So, this is directly coming from there. Okay, so, I will not go into detail on that, but now what you can do for the let us say density and the pressure, you can take this Reynolds averaging, and for the velocity and temperature you can take this power averaging. You can see that for the power average we have tilde and this double fluctuation, and for the density and pressure we have this Reynolds, this is bar plus single fluctuation or the single prime, which is basically indicating the Reynolds averaging. So, once you do that you can now, so we will use that trick. Now, you have rho u v, okay, that will be rho u tilde plus u double prime and v tilde plus v double prime. Okay. Now, you do this rho u tilde v tilde. Okay. Now, rho u, okay, don't get confused that why I am not using it, because this will be absorbed, okay, rho will be absorbed. So, rho is actually rho bar plus rho prime, okay, but I am it will be absorbed. So, you will see it shortly. Okay, so, this is rho u prime v tilde, okay, plus rho v tilde u double prime plus rho u prime u double prime v double prime. Okay. And now, you take the bar of entire thing, okay, this entire thing. Okay, so, you will have again you will see that so this I mean, or you can take a tilde of this actually. Okay. So, you will have this v double prime tilde going to 0, okay, u double prime tilde going to 0, okay, and finally, we will recover this quantity, which is we will have all this quantity going to 0, and you can have this rho u tilde and v tilde, right. So, you can basically this quantity will survive, okay, this quantity will survive, okay, and so this will be rho u double prime v double prime, and then you have bar. So, this will be rho bar u double prime v double prime tilde. Okay. So, this is all coming from this definition that we have as rho u bar equal to rho bar u tilde, that was the definition, right. So, now instead of u, you replace with u double prime v double prime. Okay. So, then we will have rho bar u double prime v double prime tilde, right. So, once again just to clarify it. Okay. So, we have this quantity and we take this normal time averaging, okay. And once you do that, you have basically you will have rho u tilde v double prime bar, okay, rho v tilde u double prime bar, okay, and then we will have rho u prime do v prime double prime bar. Okay. So, that will convert here, these two will go to 0, and there are rules on this slide which you can utilize, and please go back and do this, okay, so that you can show that this goes to 0, and finally, you have only these two terms surviving. So, which is very similar to what we had earlier. In the case of incompressible flow, we had this rho u bar v bar plus rho u prime v prime bar, okay, that is what we had in the case of incompressible flow. In the case of compressible flow, we have replaced this with tilde and rho is replaced with rho bar. Okay. So, now we will have basically the same definition. Now, instead of u prime, you have u double prime. So, we have these normal stresses, shear stresses, turbulence kinetic energy, and based on this you can also define the turbulence intensity, which is basically nothing but the fluctuations divided by the mean flow. Okay, u prime RMS divided by mean flow, or u double prime RMS divided by mean flow. This holds true in the both incompressible and compressible flow. And if you consider that my turbulence kinetic energy, which is half u prime bar square, v prime bar square, okay, w prime bar square. In this case, it will be double bar. So, if you say that my u prime bar square is similar to v prime bar square and w prime bar square, consider assume an isentropicity. So, this will be 3 by 2 u prime bar square. Okay. So, you can write this u prime bar square is 2 by 3 k. This is what is written here. So, in fact, if you use a code let us say in Fluent, you have to provide the intensity. So, from the intensity they calculate the turbulence kinetic energy by using this relation. right. So, now this is for the compressible lines, I will not go further in detail. So, now we have only these two terms. The task is to now basically get u double prime v double prime tilde rho bar. So, this is the my Reynolds stress, and you can use the similar argument like we had for the K epsilon model, that is it is related to the turbulence kinetic energy and the dissipation rate, and you can get that. Okay. Similarly, you can have this k omega model. Okay. So, instead of basically kinetic energy and the dissipation rate, we will have specific dissipation rate. So, unit will change, that will become 1 by second. Okay, it is related to something like frequency, how frequently the eddies are dissipating, okay, or disappearing, right. So, that is the k omega model, okay. And then you have variations of SST k omega. Okay. So, there are actually several models in the literature. So, this is the chart that I want to show. This is the eddy viscosity model. So, there are like linear models. Linear models means my basically tau I j r is linearly proportional to let us say S I j bar. Okay. But it can, we can also argue that okay, no, it is not linearly proportional, because again these are all models. It is let us say proportional cubically or quadratically. So, then we have different models like cubic epsilon, EARSM, V 2 omega and those kind of things, right. So, within the eddy viscosity model you have like zero equation model, that means you are not solving any extra dynamical equations, but you are modeling this both the length scale and the velocity scale, okay, by having some arguments like mixing length model are there, Baldwin-Lomax model are there. So, there is no external, I mean there is no extra equations for this. Then one equation model, which is the Spalart-Alamarez model or the SA model, very good for external dynamics. Then you can have two equation model, which is maybe the k epsilon or k omega. In the within the k epsilon you have standard model, realizable model, RNG, normalization group model and so on and so forth. The k omega we have Wilcox model, SST model, baseline model. So, these are some advanced topics. So, once you are using a turbulence model, you should know what equations you are solving and which models are good for what. Okay. Similarly, as I mentioned earlier that you can if you want, you can solve all the 6 equations, and they come under the category of Reynolds stress model. They are not the eddy viscosity model. There is no Boussinesq hypothesis here. We are solving the 6 equations, and just like we got the dynamical equations for k and epsilon, we will now have to get the dynamical equations for the Reynolds stresses, okay, 6 stresses. So, there are LLR model, HSC models for this. So, just to show you what are these, how are these models in let us say fluent and open form. Okay. So, if it is laminar, then you have just laminar, okay, there is no turbulence here. There is a Spalart-Alamarez model. Okay. So, they are present in both open form as well as fluent. It is a very common model. So, you can choose the Spalart-Alamarez model from your menu in fluent. In open form, you basically in the momentum transport file, you have to basically change it to, you have to select this, you have to write this Spalart-Alamarez. Okay. And there are several variants of SA, for example, rotation and curvature corrections and SNEG, SNOFT and so on and so forth. And this can be done in open form, because open form is open source code, so you can actually modify it. In fact, in fluent also, if you want to modify certain things, you have this UDF option, user defined function option, and that you can change. In fact, most of these like k epsilon and k omega models, you have some quantities like C mu, C epsilon 1, C epsilon 2, those values can be modified. Okay. If you want to put your own model, you have to write your own code, UDF code, that will calculate the eddy viscosity or the Reynolds stresses, and they will be put in the equations. So, in the compressible flow again we have the energy equation also. So, there also you have to put some effect of the stress, right. So, in the k epsilon you have this all these standard RNG, realizable, even low RE k epsilon model. So, corrections for the Reynolds number goes down. So, they are there in your fluent and open form both. Okay. Yes, we have several k omega models also, standard SST, then there are several variations of SST like with the curvature correction. Okay. So, if you want to use fluent, you have to choose the k omega or k omega SST. Remember, these are two different models. Okay. K omega is typically baseline k omega, and k omega SST there are some corrections in the k omega, and it is the most widely used model in the literature, okay, works for many different kind of flows, including the separation and so on and so forth. Then the flow may be transitional, it may not be completely turbulent. So, immunity may not be the maximum value that you want, it may be something between 0 and 1. Okay. So, then you have to basically get that. Uh, so, how much it is intermittent or how much it is turbulent and how much is laminar, this gamma is called the intermittency. Okay. So, there are models like gamma r theta model, also known as the length monitor model. So, they are in the fluent they call it transitional SST, in open form it is k omega SST LM. So, you have to write this in the momentum transport file or the turbulence properties file. So, there are actually two different versions of open form, one goes as V2306, V2312, and there is V9, V10, V11 and so on and so forth. So, there are different names for the files, that is very similar, but names are different. Okay. So, there are the intermittency based model, there are actually more transition models which is not mentioned in this table. You have like laminar kinetic model, and then you have some variation of SA model, SA BCM model and so on and so forth. Okay. Then there are Reynolds stress models also, they are more expensive as we mentioned earlier. Okay. And this is I mean nowadays most simulation that you do are basically using the eddy viscosity model, but yeah, you can use this if you want. Okay. They will be more expensive. So, you have like LRR model, which is Launder, Racine, Rodi model, and there are different like SSG, BRSM, and there are different kind of models available. Suppose you want to do LES or DNS kind of simulation, DES kind of simulation. Okay. So, LES is the large eddy simulation, and as we discussed earlier, large eddy simulation means your large eddies are simulated and smaller eddies are modeled. Okay. So, for the smaller eddies you have to use some model, just like use the turbulence model for every eddy in the turbulence in the RANS. In the LES you will be using basically for the very small scales, and then LES effectively you are using a filtered Navier-Stokes equations. In the RANS you basically change the equations itself, but in the LES we basically use a filter. That means, if the my eddy size is basically smaller than this, then I am going to model it, otherwise we are going to simulate using the exact Navier-Stokes equations, right. So, we have equation models like Ismay-Gorensky, okay, dynamical Ismay-Gorensky, the Weyl model, okay, the K epsilon LES. So, all these are present in either fluent or open form with names shown here. Okay. Now, DES is basically hybrid RANS and LES. Okay. So, part of the region is solved using RANS, mostly close to the wall, okay, because if you want to resolve the flow features near the wall, it will be very expensive using LES. Okay. So, in fact, there are wall model LES which are kind of a version of DES, okay, or DES is a kind of one of the kind of wall model LES. Okay. So, there are SA with the DES, there are SST with DES, and there are delayed detached eddy simulation, DES is detached eddy simulation, delayed detached eddy simulation, improved delayed detached eddy simulations. So, all these models are present in your fluent and open form. So, I am just mentioning fluent and open form, but these models are present in every single most of the software that we have, either in open source the good softwares or the commercial ones. Okay. If you use CFX, if you use maybe COMSOL, or there are maybe use SU2, you will find different implementation of these models. Okay. And finally, you have some wall treatment. So, you might want to right now, I mean nowadays you do not use a wall function because you have sufficient compute power to basically resolve near the wall. Otherwise, you have basically law of the wall of the turbulence. So, the near the wall it has a certain behavior, okay, within the boundary layer, and a little bit away from that. So, with the viscous sublayer, and then you have this law of the wall region and the log layer. So, how do you basically resolve that? So, for that also we have this kind of wall function that you can employ, and they are there in fluent as well as open form. Okay. Then if the flow is highly compressible, then you have compressibility corrections, okay, available in these models, because many of the models are derived from the incompressible flow perspective. So, you have to use that, and if you have high curvature and rotation, so just like we discussed about SARC, you can use this in either fluent or open form. Okay. So, with that we will stop here. As I mentioned earlier that it is not a full fledged CFD course. So, I did not really looked into detail about these models. If I want to discuss just the RANS models, it will take maybe 3 to 4 weeks. Okay, so I hope it gave you some flavor that how we are going to use turbulence. Let us say you want to do a simulation in a nozzle or somewhere. In fact, I just have a table here that which models are good for what. So, for example, if you want to do external dynamics, then maybe SST or SA are good. Okay. Same thing we have in this open form also. If you want to use shock or compressible flow, the SST with the compressibility correction or K omega SST can be used. I mean, both are same thing. Then if there is a transition, then you use transitional SST or K omega SST-LM. This is very common in turbo machinery flow, because incoming Reynolds number is very low, right. So, you have to use that, and if you are using let us say high fidelity simulation like LES or DES, then you have models for DES and LES. IDDES is something which is becoming very popular, improved delayed detached simulation. So, we will stop here, and in the next class we are going to basically look at some cases, we will simulate some cases using open form. Okay. I will discuss the setup, okay, and simulate some cases, and finally, we will have some discussion on the then advanced topics like the shock bond yield interactions and so on and so forth. Okay. So, we will stop here. Thank you very much.